So in this video I would like to demonstrate the phenomena of resonance on another example, which is hopefully more helps you to imagine this situation and transfer these two graphs on the left side, for example, onto a oscillation situation that we've discussed before, and also have in mind the graph or the mathematical model that's behind it. So basically in this video I will refer mainly to a swing. So this is kind of pendulum that we've had before. It is a little bit different, but still a swing on the playground is something that we can imagine very well because we've been sitting on it before and we know how it feels like. And on the right side you see the graph of the exciter in this case, and yeah, I will go into more detail shortly. The second example that I will refer to from time to time in this video will be a spring with a mass hanging on one side, and the other side is in your hand. So you can move your hand with a spring and the mass will do something in order to your movement. Let's start with the swing and the graphs that we see here. So when we are talking about the frequency of a system, I'm just checking the English word, but we have seen in an experiment before that the swing or the pendulum has a certain frequency called natural frequency, and this does not depend on the mass that we put on it. It only depends on the length of the pendulum and the small g. But this is everywhere on Earth more or less the same. So we won't consider this any longer. So for us, it's only the length of the pendulum and not the mass and not the deflection. So on the swing, this can be seen really good on a playground with various swings in a row, and they will not swing in the same phase. So it's not that every child is at every time at the same position or deflection. But if we observe this for a while, we will soon notice that the period of the oscillations of these swings are the same. So, for example, the first kid is on the very left side, and at the same time the next kid is on the very right side. But then they change the position, and the first child would be on the right side when the second child is on the left side at the same time. So the period, the time it takes for one whole oscillation is the same for every child. There is a little difference. For example, if an adult is sitting on the swing, then the frequency changes. However, this is not due to the higher weight, but the center of mass changes, and the length of the swing or the pendulum is not the length of the rope, but it's the length from the fixed point where the rope is fixed to the center of mass. So a mathematical pendulum considers the mass just in one point. So an adult is bigger, and that means that the center of mass is moving a little bit upwards, and this decreases the length of the pendulum. You will also notice when you stand up that this really changes the whole way the swing is oscillating, because then it's the mass is not so much concentrated in one area, but it's spread over a long distance, and that makes it become a physical pendulum which follows completely different equations and mathematical models that we won't discuss here. So coming back to the graphs that we see, on the first one we have YS and YE, so this is the amplitude of the swing divided by the amplitude of the exciter. And what we've seen in the experiment before is that, and here we've got the frequency of the exciter. And when that is really low, we have a ratio of both amplitudes that is 1. And that's what we've seen before, that the amplitude of both systems is more or less equal. Let's look at my second example with the spring. So you've got a spring in your hand, and on the downside there is a little mass. And when you move your hand up and down very slowly, then the spring will follow your hand, the movement of your hand, in exactly the same rhythm, and the mass will do the same. So if you move your hand slowly upwards by 1 centimeter, the mass will move upward 1 centimeter. So both systems, your hand and the mass on the spring, have the same amplitude, and they swing in phase, meaning in the same rhythm. You move upwards with almost no time delay, the mass will follow. And on the swing it's more or less the same. So if you move your legs really slowly, not much is gonna happen. Funny thing is, I've got 3 kids, and they all, well, one of them can already do it herself. My son is still, well, he's learning now, but my daughter with 3 years, she can't make the swing go up very high. And we go back a little bit. The natural frequency is also independent from the deflection. So going back to our playground, if there is a child that is only swinging with a low pace, it's got the same frequency or period as an older child that is swinging as high as possible. How can that be? The older child is going faster, so it covers a greater distance, but on its way it has more speed, and the other one is going very slowly, but it's only covering a very small distance. So they reach, for example, the equilibrium in the same time intervals. But we have already seen that the amplitude is an indicator for the energy of the oscillation. And this is quite obvious that the older child must have more energy or must have put more energy into the swing because it's the maximum velocity is a lot higher, so the kinetic energy must be higher, and also the potential energy because the deflection is higher. So the question now is, how does the exciter, this is you with your hand or with your on the swing, swinging your legs, how can you put as much energy into the swing as possible? And that's what kids don't know. And this is really difficult to learn and coordinate the legs. So if we follow the graphs here, let me just do the second one. So here, this is the delta phi, and that is the difference in the phase. That means what I've said before, 180 degrees or pi would be the situation that one system is on the very left side, at the same time the other system is on the very right side. So that's exactly opposite phase. When the phase difference is 0, that means that at each time they are in the same position. Well, at least in the equilibrium. Okay, so the amplitude might be different, but still it means the phase means, for example, not the same position, but at its maximum, the minimum, or the equilibrium at the same time at these places. Okay. So we start, that's what we've seen. When we move our legs very slowly, the swing will do the same movement, about the same amplitude. So the graphs, I've got two graphs here. One is the exciter, one that's you, and the other one is the swing or the mass. So what is happening now as we increase the frequency of the exciter? Then we see that if the ratio is increasing, that means that this one here is getting bigger, because the exciter, the amplitude of the exciter is fixed, it can't change. Your legs are fixed to a certain length, and the little wheel that we've seen in the experiment is also it's got a fixed radius, so the amplitude is can't change. So that's what we see here. So the when the frequency, and we just assume that the frequencies are the same. It's not always the case, but let's make it easier. So when we increase the frequency of the exciter, then we increase the frequency of the swing, but at the same time the amplitude increases of the swinging system. That means that we already put some energy into the swing, but it reaches a maximum and then that's it. So we've got damping effects that take a bit of energy out of the system, but also we won't be able to put the maximum energy into the swing. And you will realize very quickly that you need to move your legs with in the same rhythm that the swing is giving you, and that's its natural frequency. And we see that here in the middle of the graph. And all of a sudden the amplitude of the swing is reaching a maximum, and without damping it will go straight to infinity. That means that somehow we put energy into the swing and it does not come out. So without any damping, the amplitude would always increase. This is not possible, but still it can bring bridges to collapse, for example, or the glasses and whatnot. So now we go a little bit further down because we need an explanation for that. How is it possible that we now all of a sudden can transfer a maximum of energy? And the secret behind it is the phase difference. And we see for that case we have a phase difference of pi over 2, which is like a quarter of one full oscillation. And this can, now we need to figure out which one is before the other one or behind the other one. So let's look at the swing again. When and how do we move our legs in order to reach a good height? When the swing is at its minimum, at the equilibrium, then the movement of our legs must reach its maximum, because at that time the velocity of the swing has a maximum and we want to accelerate. So this is the moment where we have the maximum of our so in the moment or in the time where the acceleration of the swing, or where it accelerates, that's when we have to move our legs to kind of, well, we add our acceleration vector to the one of the swing, and the acceleration starts at the turning point. There it starts to accelerate towards the equilibrium. And so I will, just for a better view, change that a little bit. The question is, who is before and who is behind? If we look at the other example, we now move our hand with the spring in the natural frequency. But what comes first? The exciters, our hand. We move up our hand and the resonator will follow. That means that we are a little bit before the resonator. Okay. So here, for example. So the green graph, that's us, the exciter, with our hand or our legs, and we are at this point before the resonator is at the same position. Okay? We move in the same direction, that's very important. But when we have the resonance case, then the difference in the phase will be about here. I don't know how to change that. Okay. Actually, it's here. Okay. So when the swing is at its equilibrium position, then our movement reaches the maximum. That's in the middle, okay, at the rest position. And now we should move slowly our legs back, and then, but when the swing is at its maximum and it turns around, then we can move our legs backwards, okay? And this means that we never stop the swing, but every time we swing our legs, we transfer energy onto the swing, but it never comes back. And this is the case exactly when the explanation for the energy transfer is that the phase difference must be pi over 2. Because if you choose another rhythm, you can easily see that this is counterproductive, so that you would take out energy of the swing. That is also a possibility that we see here. So when the phase difference is pi, then the amplitude, you see here, the amplitude of the swing will even go below the one of the exciter. That means if we move our feet really fast, then the swing or the spring cannot follow anymore. And that's what my kids usually do. They think, oh, to put in as much energy as possible, I have to move my legs very fast. But that doesn't work. And it's the same with the swing on your hand. When you move your hand really quickly, the mass on the swing is too slow to follow. So it might even stay at rest, and you just move your hand up and down, you extend the spring and bring it back, but the mass is just too slow to follow. So in this case, the amplitude is going down again, well, maybe to 0, but and that's when we have a high frequency. Okay. I hope this video helped you to understand the phenomena a bit better, to understand to be able to interpret the graphs that are in the mission, and to recognize the mathematical model behind it. So very down here you see the 0.3 sine. Yeah, the 0.3 is the amplitude. 4.8 is the factor that determines the frequency, and the 3.1 is shifting the curve to the right, and is responsible then in our model for the phase difference. Yeah, it's 0. The phase is 0 for the first graph, and the difference can be put into the model by adding just a number here.